Today on How It's Made. Pistons. This should spark some interest. Paint rollers. We bring you wall-to-wall coverage. Parachutes. A story with strings attached. And chimneys. We smoke out a factory that makes them. But first... Pistons are key to the internal combustion process that drives engines. A piston is a plug that slides up and down inside each cylinder, compressing gas and air ignited by a spark plug. The resulting energy turns the crankshaft and drives the engine. This company makes 9,000 different types of pistons. For everything from dirt bikes to car engines. A piston starts out as a 3-metre-long aluminium rod. Aluminium is ideal because it's a lightweight, rust-resistant and easy-to-cut metal. A rotary saw slices the rod into slugs, the length of which can be changed by adjusting the feeder machine to push the rod at different intervals. This piston model requires 7-centimetre slugs. The factory recycles excess aluminium shavings. The punch press and die are preheated to 426 degrees Celsius, the temperature required to forge the slugs. The slugs are brought to the same temperature in an oven. The punch applies 2,000 tons of pressure to form it into the initial shape of the piston. About 1 in 10 forgings are dunked in water to check for defects. To make forging easier, they pre-lubricate the slugs before heating them. That's why the slug flames up when struck by the press. It only takes 2 seconds for the press to do its job. But the forgings are so hot, they need at least an hour to cool before the next step. Workers heat the forgings twice more. The first time at a very high heat to strengthen the metal. The second time at a lower heat to stabilize it. Now, they insert each slug in a lathe to give the forging the correct shape for machines that handle it later. These small holes allow oil to flow through to lubricate the piston when it's in use. Another lathe reduces the diameter by 3 millimeters. The same machine then cuts 3 grooves, 2 for compression rings and another for an oil control ring. These rings help the piston glide and enable it to provide an airtight seal. This hole is for the wrist pin, which will attach the piston to the connecting rod. A milling machine then shaves off up to 2 centimeters of metal from 2 sides of the piston to reduce the overall weight. The white liquid is lubricant to cool the area during cutting. Another milling machine cuts away part of what they call the dome. This way, it'll clear other parts when moving inside the cylinder. The piston must be just the right shape and size. Some of them move up and down as much as 6,000 times per minute when the engine is running. Next, a lathe shaves a hair width more of the metal from the outside. This cut enables the piston to expand slightly when the heat builds up inside the cylinder. An automated drill makes 2 intersecting oil drain holes to enhance lubrication of the wrist pin. Another machine now engraves model and production data. Here, a worker removes sharp edges created during previous operations. He then uses a belt sander to further smooth out the surface. Sharp edges could damage the cylinder walls. This cutting machine shaves off a bit of metal inside the pinhole, so the wrist pin will fit snugly inside. Once the cutting's complete, high-pressure jets spray the pistons with hot deionized water. This cleaning removes all traces of lubricant and oil. And after a blow-dry with an air gun, these pistons are ready to go through their ups and downs. Norman Breakey, a Canadian, invented the paint roller in 1940. It revolutionized painting, but Breakey never got rich because he lacked the financial means to defend his patent. Alongside the brush, the paint roller, with its replaceable cylindrical refill, has become the primary painting tool. The refill is a tube covered in fabric made from either polyester fibre or lint-free acrylic and nylon fibre. Regardless of fabric, all refills are made the same way. The fabric is processed into a 7.3 centimetre wide strip. It goes into a machine called an automatic tube winder. It first applies epoxy glue to the surface of PVC plastic tubes. As a tension bar pulls the fabric strip taut, the machine winds the fabric around a tube. An air jet pushes aside the wound fabric to avoid bumps as more is applied. Once the tube is covered with fabric, the machine simultaneously wraps the end and the start of the next tube in masking tape. Once the glue is dried for 8 hours, the tubes enter a machine that cuts them into several refills. The tube spins as it passes, so one small cut is enough to sever it. One tube produces 9 19-centimetre long refills or 7 24-centimetre long refills, the two standard sizes on the market. The next machine first runs a wire brush against the fabric. This lifts and fluffs the pile. Then a beveled edge is made on each end. To fluff the fabric further, it's spun at 3,500 RPM. During all these operations, a vacuum sucks away loose fibres. Meanwhile, the paint roller handles take shape. An injection moulding machine shoots molten plastic into handle-shaped cavities. A built-in cooling system hardens the plastic within seconds. The handles are made of polypropylene, a tough thermoplastic, and some coloured polyethylene, a lightweight thermoplastic. Now that the handles and refills are made, it's just a matter of assembling them. These plastic bearings hold the components together. The assembly is entirely automated. The bottom bearing goes on first. It rests against the part called the shoulder. Next, the refill. The bottom bearing slots right into the open end of the tube. Now the top bearing goes on. A metal clip locks the bearings and roller in place. And voila, a 7.6 centimetre roller for painting windows and trims. This factory also makes disposable plastic paint trays and tray liners. They're made of polyethylene terephthalate, PET for short, a type of plastic that's strong yet flexible. This thermoform machine heats a PET sheet, then vacuums it into a tray-shaped mould. fans cool and harden the plastic. This cycle takes less than a minute. The moulded sheets go into a cutter. It removes the trays in one slice. The factory grinds up the leftover plastic and sends it back to the supplier for recycling. This factory also makes roller refills for applying solvents. Paint rollers, spreading happiness and paint wherever they go. Coming up on How It's Made, parachutes. Don't jump till you've seen this one. And chimneys. Stacks of them. See you after the break. Welcome back to How It's Made. When aeroplanes first took off, so did parachutes as the best form of escape. Today's aerodynamic lightweight chutes enable cargo and people to descend safely and land right on target. Let's drop into the factory to see how they're made. This company makes military parachutes. Each one has a 9-meter wingspan and carries up to 200 kilograms. Making the chute's canopy starts with a rugged woven nylon fabric with nylon ribbing. This light table lets a worker detect any flaws in the fabric. The alignment between the ribbing must be consistent. They test the fabric by pulling the material until it rips. To pass, the fabric must withstand a minimum of 20 kilos of pulling force. A laser cuts out the parachute parts, 30 to 100 of them, depending on the model. A vacuum system stabilizes the fabric by sucking it to the table during cutting. The fabric is usually silver-colored to blend in against the daytime sky. A seamstress now sews on nylon tape to attach the parts and reinforce the seams. Some panels have holes about the size of a dinner plate to funnel air between the two layers of the canopy and keep it rigid during flight. Once they've finished sewing, workers inspect the stitching. Every 2.5 centimeters of stitching must have between 7 and 10 stitches. If the stitching is too close or too far apart, the fabric could rip. And that's the last thing you want when your chute is descending at a rate of up to 4 meters per second. So they mark any problem spots with a red ribbon and re-sew them. Here, a worker sews nylon tape to reinforce an area called a flare, which is a triangular patch of nylon reinforced with silicone coating. She loops the tape at one end of the flare's points to later insert what's called a suspension line. The 60 lines link the 60 flares on the canopy to the jumper's harness. To reinforce each flare, she sews 42 zigzag stitches in a 2.5 centimeter area. The nylon suspension line arrives on spools, so workers use this machine to stretch it straight. A worker marks off up to 4.5 meters per line and cuts it on an angle to reduce fraying. Workers later sew the ends into loops so they can attach each one to the loop on the flares. A worker makes a lark's head knot in each line and ties it to a flare. This type of knot is easy to undo if a line needs replacing. Connecting the 60 lines to the canopy's 60 flares takes about 2 hours. Only after all these knots are secure can they pack the chute into the backpack and ship it to the customer. The nylon backpack has two identical parachutes, the main chute and a reserve. This worker is sewing the panels that'll encase the reserve chute. Extra stitching reinforces the straps. Strict guidelines must be followed when packing the chute. The ends must be rolled, then the rest folded into layers. Before each jump, the lines must be untangled and checked for any tears from the previous jump. The lines and the canopy are inserted into the pack. Pulling on this red handle deploys the main chute. The yellow handle is for the reserve chute. There are straps over the shoulders, chest, belly and legs. Finally, 3 buckles attach the harness to the jumper. Good luck! Chimneys vent hot gases or smoke from your fireplace to the outside. Some types also channel air to the fire to keep it burning. Although the concept's very old, today's chimneys have come a long way, and making them is an exhausting business. This company makes chimneys for gas-fired and wood-burning fireplaces. A chimney's inner chamber is called a flue. For a wood-burning fireplace, they make the flue from stainless steel. Workers unwind a sheet, then slice it to the size of the flue section they're making. The sections are up to 25 centimetres wide and 1.2 metres long. They assemble as many as they need to make a complete chimney. Here, a worker folds the edges in opposite directions, which will enable them to interlock. Rollers then curl the sheet into a cylinder. The metal's only about as thick as 4 pieces of paper stacked together. This keeps the chimney lightweight. They weld together the top and bottom ends, and a roller flattens the welded seam. They insert the bottom of the flue between 2 rollers. They form a ridge to which a coupler will later attach. They crimp the metal at the top so it can also hold a coupler. To make top-end couplers, a die punches the shape from lubricated sheets of stainless steel. A robotic arm then suctions out the coupler and places it into another machine that cuts threads into the sides of it. These threads enable the chimney sections to twist and lock together. To attach the coupler, a worker mounts it on top of the flue. A roller then pushes against the flue and the coupler. This expands the metal and secures the pieces together. Now, to join the flue with the outer casing, an 8-sided die pushes out against the coupler to attach it to the flue and the casing. They insulate the chimney with shredded ceramic fibre that can withstand a temperature of over 1,000 degrees Celsius. Workers feed the fibre into a machine that packs it into the cavity between the flue and the casing. The machine then moves the chimney to another station, where it twists a coupler to the bottom end to close the cavity. After a quick brushing to remove any fibre dust, a mechanical arm lifts the chimney and moves it to be boxed and shipped. A gas-burning fireplace generates less heat and fewer corrosive gases, so the chimney flue is made of aluminium-coated steel and the casing of a zinc aluminium alloy. More affordable materials, yet still well above safety standards. The airspace between the flue and the casing provides the required insulation. A worker places the flue inside an automated welder. It fuses the edges with a laser that's as thin as a human hair. This is called a butt laser weld, because the machine butts the edges together and bonds them. Next, an 8-sided die indents the section with 3 ridges. A component will fit into these indentations later. Here, a machine creates a star-shaped component called a spacer. They use 2 of them to center the flue in the casing. A worker installs a spacer at each end of the flue. Then he inserts the flue into the casing and twists it to lock the spacers into ridges. This connects and aligns the chimney sections. The tops of the chimneys have steel rain caps. They let smoke and gases vent but keep the rain out, ensuring that where there's smoke, there is indeed still fire. So, whether you're the type who likes to tinker with your engine, or maybe you're a DIY devotee, or a person who prefers to plummet from the sky, now you know how it's made.